Okay, so today we are going to learn about another topic, generative adversarial networks. So, what is scans? In AI, like in normal AI application, we are enabling the computer to perform tasks. Like we are training some machine learning model, we are training them to perform some task. But in Gen AI, we are enabling the machines to think like humans, to work like humans. Okay, then this generative adversarial network is a type of deep learning model. It consists of two main parts. One is generator, another is discriminator, and they are trained in a competitive manner. Okay, so the main goal of GANs is to generate a completely new data which is not actually present. So it is, you can say, it is to generate fake data which looks like real data. So like this is basically the like if you see ChatGPT, okay, you know these all are social apps. Okay, so I'm just telling the importance of these ChatGPTs because they also use these kind of methodologies. In just this much 2 months, it reached 1 million users, while others took so long. So you can see the increasing interest in AI applications, in LLMs, in these generation like text generation or image generation, and the main people who work to develop these are researchers in various universities, then some government institutions, companies, and there are many open source communities which are continuously updating these libraries to work more efficiently. So how this works? First, in training, we will have some training data. Suppose in this one, you can see we have some boat, we have some trees, water lily, and there are many more images will be there. So we will send it to a model. The model will be trained on these images. Then we will be asking some prompt. For example, we are saying that wide angle shot from below of a female astronaut. Okay, so sorry. So what the model is generating, we give some prompt to some trained model and it will be generating some new content. Now this content is completely different. Like this is a fake data. This is not a real one. You can also generate conversation. It is not like you can do only image generation. You can do audio generation. You can do text generation like you do in ChatGPT. Okay, uh, you can create videos as well. So these are truly very useful. So what is the structure of GANs? As I have said, it consists of two components, generator and discriminator. Now, what is the work of this generator? We will be sending some noise, like this is random noise. Okay, so we will be sending this to generator, which will be a neural network, and this will generate some image. So it will be a fake image. Okay, so the discriminator will try to figure out if this image is fake or real. So what will be the generator's task? To produce this image as real as much that discriminator won't be able to recognize if it is real or fake. Okay, so the main task of generator is to fool the discriminator. And what is the role of discriminator? To distinguish if the image or any kind of sample, audio sample, whatever it is it is coming from the training set or it is created by generator. This is the actual sample training set. Okay, we are taking a sample from it. So its main task is to correctly identify the difference between fake and real. So these two, this generator and discriminator, these work in an opposite manner, or you can say in a competitive manner, to produce images, fake images which look like real. So, and like we have learned in previous also, we do fine tuning by using back network. So same things happen here as well. So I think this part will be the main part. This is just a sample data set. We will work on this example as well in our coding part. So there is some MNIST data set. As you can see, many images of clothes. Okay, so this is our real sample. Okay, so and like before, I was saying that we have some random noise. So we send this random noise to some neural network. Okay, the input layer has 100 nodes, and because this is 28 by 28 cross data set, so the dimension of this one will be this much. Okay, so we have to also give the dimension same. So in the output layer, we have 28 by 28 nodes to produce this same sample, similar dimension sample. So this is a fake sample, this is a real sample. This is our generator. We generated this fake sample. So this is our discriminator. So discriminator is again consisting of neural network. The input layer will have these 28 by 28 nodes. Okay, because this image has this dimension. So this will be having total 784 neurons in the first layer, and then it output layer, it just have to tell whether it is fake or real. So it will have only one node, yes or no. Okay, so this is an example of how the actual workflow will look like. So this is the kind of same thing, but just how we are training the discriminator. So in discriminator, there is some noise vector from which generator is generating some image. It has y will be equal to 0 because this is fake data. From the real instance, y will be equal to 1. And then these both will be sent to discriminator, and discriminator will see if it is fake or real. This is the training of discriminator. Now how we will do training of generator? It will try to say that these fake examples are real. It will say, okay, y is equal to 1. This is the real example. So now the discriminator job will to see if it is really fake or real. Okay, so this is an interesting part, and also this discriminator and generator, these are trained separately. These are not trained parallelly. Like at a time, either discriminator will be trained or generator will be trained. So this is the loss function. As in the output, we can have two possible outputs, yes or no. So as we have studied in the first lecture of deep learning, that for a binary classification, we have binary cross entropy as loss function. So this was the formula, if you could remember, for this binary cross entropy loss function. Okay, so for the data coming from actual sample, this is our real sample that will be having label 1, and this will be the prediction when you send it to the discriminator, this goes for discriminator. Okay, so this is discriminator. So when you send this real data x to the discriminator, then what will be the prediction coming from the discriminator? That will be y hat. Prediction from this discriminator, y hat, and this is y actual data. So when you put this back to the this one, this will be 0, and sorry, when you, yes, when you put back to this one, this will be 0. Okay, and y will be 1, and log y hat will become log dx. Okay, this is data coming from the real sample. Now data coming from the generator, which is fake data, that will have label y is equal to 0, and y hat will be, this is coming from the generator. G is for generator. Okay, so this generator is having, this corresponds to some noise vector z, and generator is working on it, producing some image, and then this image will be sent to discriminator. So y hat is probability from discriminator on the images generated by generator, fake images. So for this one, for data coming from generator, we will have y is equal to 0. So this first term will be 0 now. Okay. And the second term will have 1 minus y is 1. Log 1 minus y hat will be replaced by this value. Okay. So what will be the objective of discriminator? To maximize these two terms. Actually here there should be a negative here. Okay. So, or you can say to minimize both the loss functions so that it can accurately identify whether it is a fake data or real data. That is the main task of discriminator. What will be the objective of generator? The objective of generator is to produce as much as like the produce the data which will be very close to the actual one. So in that one, like this term won't come into account for generator because this is coming from the real data, and as we have uh, seen here that while training the generator, we only look at the data coming from the fake samples. So this loss term won't be here. Generator will have only this loss term, and its function will be completely opposite. If it is trying to maximize these two terms, then generator will try to minimize these one because these are working in a competitive manner. Next, what will be the optimal value of these generators and discriminators? So for a fixed G, optimal discriminator, like this will be your discriminator. This is your probability distribution from original data. This is probability distribution from generator. So it will try to maximize this term. This will be the discriminator task, that it will maximize this one. Okay. The role of generator is reverse of discriminator. So the optimal value for this will be when PG, the distribution for coming from the generator, is similar to original data. That means PG is equal to P data. At this point, this was calculated. Okay, you can check the paper. I will show you the paper link as well in the next slide. But at this point, dj star will be equal to like if you put pj is equal to p data, then it will be 1 by 2. Okay, so it is 0.5. So you can see actually when both of these have values 0.5, both the discriminator and generator, then we can say, okay, it is not able to now distinguish between fake and real images because it has the value 0.5. So this was the paper I was talking about on GANs. So this is a figure taken from this paper. Okay, so in the first one, this is noise. Okay, it's the real one. Okay, so this dotted line shows you the real data. This blue line is coming from the discriminator, and this green line is coming from the generator. So you can see initially the noise vector is giving this kind of distribution. It is somewhat more focused here, so it has a peak here in generator, and our actual distribution was like this, and discriminator was giving some value like this. So at this point it was okay to producing the sample, like discriminator was telling actually like here the this data is real and this data is like here it is coming close to the actual value, so this one is real. So you can imagine that generator is trying to produce some samples from noise. So we can expect that initially generator's loss function will be huge because generator won't be able to do so good because it is just coming from the noise, right? But discriminators like recognition will be good. Discriminator could easily recognize between real and fake samples. But then we trained our generator. So it like up and down, but then we trained the discriminator. It was very good in identifying real and fake samples. After this, we started training the generator. Okay, so you can see that the distribution is coming close to the actual one. And after many trainings, okay, the actual sample and the your generator generated sample will have almost same distribution. This is the ideal case. Okay, and generator will give same value, like it won't be able to identify whether it is fake or real. So these are some examples. So in discriminator, we try to fool the by giving the images of bagels and puppies. Okay, so it may sometimes hallucinate as well if there will be less training. Okay, so but if you give good amount of training data, then it can easily recognize that it is a puppy. Now there is one more most common problem in GANs is mode collapse. So when this happens, when generator learns to produce a limited variety of outputs instead of capturing the diversity of the real data distribution. Okay, so suppose you have many images of animals. Okay, so like you have images of cats, dogs, birds. So the generator like finds that when it is giving the images of cats, suppose the discriminator is not able to distinguish between real and fake. So here, what we keep our main target is that is discriminator as possible as we try to fool the discriminator. So as soon as generator sees that, okay, these images, like cat's images, discriminator is not able to distinguish, it will start producing only those kind of images. Okay, because its main task is to fool the discriminator. So, and discriminator will also provide feedback that yes, you are like these are generating well. So in this case, you can't actually capture the diversity. You will just say, okay, you will keep training on the same images and you say, okay, these are the images that we have trained on. So there are many strategies to mitigate this mode collapse problem. One common technique is to use this to help stabilize training. Okay, so there are many different versions of GANs, like deep convolutional GAN, conditional, the WGAN which we just started, least square, big GANs for big data sets, stack GANs. So you can learn about all these. For now, I have just give you overview. What is GANs? What are its use and the basic architecture. But when you go into more detailed work on more advanced problems, then you will see that you may need to use this advanced versions of GANs. So are there any doubts still here? If not, then we can move to the coding part. Oh, sorry, 1 second. I need to charge my laptop. Okay. So as I have said, we will be working with that MNIST dataset for which I have showed you the example. So first we load that data, okay, and we apply some transformations. Too sharp. Maybe I will leave it if I can't work it out. Okay, leave it then. So we will apply some kind of transformation here. We are basically normalizing the images with giving mean is equal to 0.5 and standard deviation is also 0.5. So now all the pixel values in the images will have values between -1 and 1 by doing this normalization. So you can see that the first element in this set has label 5. So this was a different one downloaded. This one is actually not the that images of clothes. It is actually numbers, which I will show you now. So let me first show you. So this is a data like this. Okay, so you can get an idea. Then I will start explaining from the very beginning. So these will have images like these for numbers between 0 to 9. So first we will see what is the first element. It has label 5, that it is a number 5. Then we show this is a 28 by 28 dimension data. So I'm just showing the elements from 10 to 15. Okay. Then we are saying what is the minimum and maximum value in this tensor. So as we have normalized this with mean and standard deviation, so the minimum and maximum value will be between -1 and 1. Okay. So we are printing this image shape. Then to see the image, how it is looking like, to see our data, we are just denormalizing just to see our data. Okay. And then plotting it using matplotlib. So we can say that label is 5 and you can see it. Then we are defining a data loader, giving batch size is equal to 100. And for this data loader also, we are seeing the first image, like how it is coming. So it is a 0. Then we are defining the device configuration. This is done to, like, if you want to use your GPU to fasten the training process, then you can do this thing. Okay. So if GPU will be available, it will connect to GPU. Otherwise, it will stay with CPU only. So now, as I have said, that image size is 28 cross 28. So that means if you multiply those numbers, it will be 784. Then we define a hidden size. This is the actually number of neurons in the hidden layers. So here we are defining the discriminator, and as I have said that discriminator is nothing but it is made up of a neural network. So as we have discussed that there could be many neurons and many hidden layers. So we say 256 is the number of neurons. Now we define the full architecture of the discriminator, like how this will have be. So first we will give image size as input. Like in the first layer, we will have this one, and then this will be the number of neurons. Okay, then we are using this leaky ReLU as an activation function. I hope you remember what is leaky ReLU. Anyone want to tell what is leaky ReLU? Okay, so we studied that in leaky ReLU, if the output coming from the integration function is less than 0, then it will be multiplied by some number alpha. Okay, so alpha into x. So I think I can show you in first day. It will be better. Yes. So leaky ReLU was, if it is greater than 0, then it will be x, and for less than 0, for this region, it will be ay, or you can say alpha x. Okay, so that point 2 you were saying in that bracket, that was alpha value. So we are giving this alpha value here. Okay, so this alpha value is 0.2. And then we defined another layer, or the second layer. So this will again have these many neurons, and this is the activation function. And then we define the final layer. And in the final layer, as this is a discriminator, and I have told you in the discriminator, in the final stage, we will be having only yes or no. So it will have output only one neuron, and we apply sigmoid function, because the sigmoid function, like this is also has been discussed before, that sigmoid is the activation function for binary categorization problem, where we have two categories. Then we define generator in a similar way, a bit different. So here we start with latent size. So what is this latent size? We have seen that first it is generated from some noise. So this is the size of that noise vector. Okay, so This is the size of that noise vector. So for now we have kept it as small because like this is noise. So if you give a smaller number, it will force the generator and discriminator to produce more like real life images and not overfitting. Okay, so if you give large size, it may overfit. It may lead to overfitting. So you can think about that, how it will be doing that. It is interesting to see these things. So yes, the hidden sizes again we have defined 256. Here we are giving this ReLU. Here we are not using leaky ReLU. You can try with that. There is no issue with trying. Okay, I just didn't do it here, but yes, you are welcome to try here leaky ReLU as well and see if there are any changes. So this is the final layer. So in the final layer, we will be giving image size, that is 784. As we have seen in that data set in our this one, that in the final one we will be giving 28 cross 28 layer. So similar to that, we will be giving here image size as the output in the last layer. And here we are applying the last function as 10x function because it will provide the values in the range -1 and 1. And since our generated images will have also pixel values between -1 and 1 as they are normalized. So this is a good choice for activation function in this generator's last layer. So this is just a visualization how our first noise vector will look like. So we are reshaping it to, because it will be a 784 size vector. So we are reshaping it to the actual dimension which we want to compare, that is 28 cross 28, not a straight linear vector of dimension 784. Okay, so you can see it's just noise. You can't see anything. No numbers are here. So second image is also like that. You can see you have to train a lot for the generator. So we start the training. First we will define how we'll do discriminator training. So this is binary categorization and trophy loss, as we have also seen in the presentation, how that will work. So we are giving the optimization as Adam. Okay, learning rate we are defining as this one. Then we are defining a function which will set to optimizer and gradient. There will be set reset to their like zero values to ensure that the gradients are calculated from the current batch and they are not accumulated from the previous batches as well. Okay, so then we define how to train our discriminator. So there will be some real labels which will be given one value and the fake labels will be given zero value. Okay, then we apply this D corresponds to, you remember we have defined this D here. This is the D, our neural network, and this is G. You remember these things, that these are our neural network for discriminator and generator. So we say that when we apply D on images, then it will give some output and we will calculate our loss function outputs with the real labels. Okay, so these images will be coming from the samples, real samples. Okay, so this is the loss function for real images. Then in similar way, we this is to produce the random function, like which was having a latent size of 64. Okay, so generator G is for generator neural network. So we are this generator is working on this distribution and it will be producing some fake images. We are again sending these images to the discriminator and it will be calculating the loss for fake images. Okay, so the total loss will function will be d loss plus d loss real plus d loss fake. As we have seen also from this presentation, that the loss function will be the image, the data coming from the real sample and from the generator. So it is similar to that, combining the losses for both the real images and the fake images for the discriminator. And this is the like computing gradients. First reset it, then compute it for the current batch, and then you use back propagation, like we use in neural networks to set the weights and biases. So this is the discriminator training. Okay, for now we are just defining the function. Then we will come to generator training. So here again we are using Adam optimizer. Learning rate is same as before. So how the generator will be trained? Here we will have only one thing, only the values coming from the generator. So again we are defining the distribution. Then we are producing fake image using generator. This time we are giving these labels 1. Yeah, you remember in this one we were giving labels 1 to the generator generated images, and then we are sending it to the discriminator. Okay, so see, discriminator will work on these fake images and it will compare with the labels. So with this, get the generator loss. So this is like to see the image. First, we will see the actual image, how it looks like. Okay. Then also we are saying that we will save the images at 1 second. Let me connect so that I can show you. So yes, we are defining a function to save the fake images to see how this generator is working, how it is improving. So we are saving this fake image. This is an optional step. If you want to save, you can, or you can just leave it as such. I'm saving to show you how these will look like. So the first fake image at 0th epoch will look like this. Then we define the number of epochs. Okay, these are some empty list we are defining, and then we start the actual training. Earlier we have only defined the function for training generator and discriminator. So here we will train the discriminator and generator. In data loader, we have actual values. As you remember, we have above we have defined this data loader for our MNIST data set. So where was it? Yes, here. MNIST data set where we were giving batch size 100. So these are the actual images. Okay, so train discriminator. We are training the discriminator on actual images. Okay, and then glog train generator. Generator doesn't need any input because while defining this function also, we will be generating the fake images using this random distribution. Okay, so we don't need any input in the generator. It will work on these fake images. So here we will train the generator and discriminator. And after every 200 iterations in single epoch, so in a single epoch, we will have total 600 iterations, and every 200, we are saying that add the loss function to the list. So and show it here. So yes, and save fake images after completing one epoch. So you can see in the beginning, we have discriminator loss is 1. is equal to 0.0535 and generator loss is this much. So as I have said that initially discriminator will work very well because the generator loss will be high. Generator won't be able to recognize to produce the real like samples. It is just noise. So generator loss will be high while discriminator loss will be low because it is very good in identifying the real and fake samples. So if you want to see the first one we have already seen, you can start seeing the second one. How after the second epoch you can still see there is noise, nothing is there. So let's see how it is going. You can see the slowly discriminator loss is increasing and generator loss slowly starts decreasing. After many epochs it will decrease. So it is coming to 2, 2, 1, 3, 1. Okay, so let's see how it is after 100 epochs. So we can see the 100th image. Can see uh, you can see some numbers now. Okay, then at this point we have discriminator loss is this much and generator loss is decreased from 5 to it comes around 2, 1.9 to be precise. So again you can see after 200 200 steps, 200 epochs how it looks like. So at 200 you can see these are more clear. This is at 100, still some blurred. Now it is more clear. Some are still blurred. Some words are still it is better. So yes, here you can see that after training for 300 epochs, yes, so after 300 epochs, our generator loss is this much. Okay, and our discriminator loss is 1.0116. And we can see how it looks like at 300. You can do more. Actually, it is a computationally heavy process. So I stopped at this part. Still some digits are blurred. So yes, you can have more epochs. See if it is improving. So this is the 300 image. So also that remember to save these models because it's tough to run them again and again. They take a lot of memory and GPU power. So we are plotting these loss functions. So you can see that generator's loss is how it is decreasing with the epochs. Okay. And this generator, this score for real and fake, the number of epochs, it is coming close to zero point 0.5. Not exactly close, but it is, yes, it is coming close to 0 0.5. So yes, in this way you can like generate fake images. Okay, using these kind of training, using more epochs, you can generate even better images. So I just want to show you one website which they have used this model and they have produced very good images of, you can see this person doesn't exist.com. Actually, it will generate the images of persons who actually don't exist. But you can't tell from the look of this person that this is not an actual person. Okay, we can see the sharpness and everything. It it can also generate accessories. These every time you reload the website or open this website, it will generate some new image. So you can never distinguish between real and fake. Yes, so this is all from my side for today. Any questions so far? Today's session was a bit short. I didn't keep it very long. In this session, we have learned about GANs, what is generator and what is discriminator, what are their main roles, and how you can generate fake images using these generator and discriminator. If there audience, maybe we can stop the session. So hope you have learned a lot in these sessions, and you will now learn more, because each time you will learn, you will get to learn new things. So whenever I am learning, each time I'm studying these things, I find that okay, something is new, something really interesting. So yes, please try and work on